In this series of videos, we're going to be going over first-order differential equations. So some topics we're going to be going over today are homogeneous differential equations, so things of the form dx dt is equal to lambda x of t, constant input differential equations, so things of the form dx dt is equal to lambda x of t plus a constant u, and functional input differential equations, which are equations of the form dx dt is equal to lambda x of t plus u of t. So the first question I want to ask is, what is a differential equation? So a differential equation is an equation that relates one or more functions with their derivatives. So let's just say we have a function here, x of t. It has some waveform like this. And the most fundamental example of a differential equation would be something of the form the derivative of x of t is equal to x of t. So whenever we talk about differential equations, we're always interested in something called the solution. So the solution is a function xp of t, which makes this first differential equation 1, right here, true for all values of t. So here the solution would be x of t is equal to e to the t. And we can kind of see this by saying, hey, what is the derivative of e to the t? The derivative of e to the t is in fact e to the t, and that is equal to x of t. So now we're going to take a look at an example problem and kind of look at 3 different ways to solve this problem. So let's say we have the derivative of x of t is equal to 7x of t, and we know the initial condition is x of 0 is equal to 3. So the first thing we can try is integration. So by integration, I mean, let's say that dx dt is equal to 7x. Then we can divide by x and say dx over x is equal to 7 dt. And if we integrate both sides, we will get something of the form the log of x is equal to 7t plus c. Now we plug our initial condition back in, meaning since we already know that x of 0 is equal to 3, we plug in 0 to get log of 3 is equal to 7 times 0 plus c, and this tells us that c is in fact equal to the log of 3. So now we know that the log of x is equal to 7t plus the log of 3, and if we exponentiate both sides, meaning I take e to the to both sides, I'll get something of the form x is equal to e to the 7t plus log 3, which is then equal to e to the log 3 times e to the 7t, and I'll end up with 3 e to the 7t. Now we're going to take a look at the guess and check method. So the guess and check method is saying that if we have a differential equation of the form dx dt is equal to 7x of t, I in fact know that my solution will always be of the form x of t is equal to k e to the 7t, where k is just some constant. So the first thing we need to do with guess and check is to first verify our guess works. So verify the guess. And the way we verify the guess is by saying, given this x of t equal to k e to the 7t, we just take the derivative. That will be 7k e to the 7t, which is just equal to 7 times k e to the 7t, which is indeed 7x of t. So now we've showed the guess actually works. The next thing we do is plug in the initial condition. We already know the initial condition is x of 0 is equal to 3 over here. So then we just say x of 0 is equal to k e to the 7 times 0, which is just equal to k e to the 0, or just k, and we know that's equal to 3. Therefore, we can say that our solution, xp of t, is equal to 3 e to the 7t. So now I'm going to come up with a generalized formula for any differential equation of the form the derivative of x of t is equal to lambda x of t with an initial condition x of 0 is equal to x sub 0, And remember that lambda and x sub 0 are both constants. So we should take the idea we know from guess and check, where we know that x of t is equal to k e to the lambda t. We can again take the derivative and verify that the guess indeed works. I'm not actually going to do that. And then we plug in x sub 0 is equal to k, which is equal to x sub 0. So we should now get the general form xp of t, and by p I mean particular, is equal to x sub 0 e to the lambda t. We have now gone over 3 different ways to solve the same differential equation, the derivative of x of t is equal to 7x of t, with initial condition x of 0 equals 3. With integration, we used the fundamental ideas from calculus, where we write dx dt is equal to 7x of t. We separated the variables, took the integral on both sides, and then got to the direct solution of 3 e to the 7t. One of the problems with the integration method is whether or not we can actually separate the variables. So for example, if we had the differential equation, the second derivative of x plus 7 the derivative of x plus 5x is equal to 3, then separating these variables into something we can integrate will often be very difficult or at times impossible. With the guess and check method, we took a test solution, or test function, k e to the 7t, verified the guess works, and then plugged in the initial condition to get the same solution, 3 e to the 7t. With guess and check, one of the concerns we should be making is whether or not our guess is in fact the right guess, and also how we should be making our guesses. And sometimes the difficulty in guess and check will come in what is a good guess and verifying the guess works. Taking the derivative may be more difficult than anticipated. Lastly, we have a generalized formula for any differential equation of the form the derivative of x of t is equal to lambda x of t with initial condition x of 0 equals x sub 0. We said the particular solution xp of t is equal to x sub 0 e to the lambda t. Generalized formulas are really great, but it only works for this specific differential equation. And once we build more difficult differential equations, we won't see them in this class, but there will be differential equations where there will be no generalized formula. We'll take a look at a quick example now, which is not in the form we saw in the previous examples. So let's say we have a differential equation of the form 2 dx dt plus 4x is equal to 0 with initial condition x of 0 is equal to 2. So now we want to put this in the form the derivative of x of t is equal to lambda x of t with initial condition x sub 0 is equal to x sub 0. So all we need to do is move everything to one side. We want to move the 4x of t to the other side. So we'll get minus 4x of t, and we'll divide by 2 to get dx dt is equal to minus 2x of t, and the initial condition will be x of 0 is equal to 2. And then using the formula from the previous section, we know that the particular solution will be 2e to the minus 2t. Now we will take a look at differential equations of the form dx dt is equal to lambda x of t plus some constant u, with initial condition x of 0 is equal to x sub 0. So an example of a differential equation like this is something of the form dx dt is equal to 2x of t plus 3, with initial condition x of 0 is equal to 4. The first way in which we're going to solve this differential equation is to use something called change of variables. So we're going to define a new variable, z of t, which is equal to x of t plus u over lambda. And we're going to write a new differential equation in terms of z. And the way we do this, we're going to first take the derivative of z. And since u over lambda is a constant, dz dt will in fact be equal to dx of dt. Then we want to look at the right-hand side. We see lambda x of t plus u, and we can actually realize that lambda x of t plus u is the same as lambda times x of t plus u over lambda. Which is in fact just lambda z of t. Therefore, we can write a new differential equation. The derivative of z is equal to lambda z of t. Its initial condition, z of 0, will then be x of 0 plus u over lambda. Now we already know how to solve this differential equation since it's of the form dz dt is equal to lambda z with initial condition. So its solution, zp of t, will in fact be equal to x sub 0 plus u over lambda e to the lambda t. Now, our original differential equation was in terms of x, but our current differential equation is in terms of z. So once we changed variables to z, we have to change back into x. So x of t is equal to z of t minus u over lambda. So given zp of t, we can say xp of t is equal to zp of t minus u over lambda, or x of 0 e to the lambda t plus u over lambda e to the lambda t minus 1. Now the second method we're going to use is again guess and check. So with the guess and check method from the last time, we need to remember what our test function is. So for this specific differential equation, I'm going to tell you right now that our test function is k1 e to the lambda t plus k2. So if we look at our solution from change of variables from the previous part, we can see that this actually can be rewritten as x of 0 plus u over lambda e to the lambda t minus u over lambda. So this quantity here will be k1, this quantity here will be k2. So with our guess and check method, we now need to take the derivative and see that our guess actually works. So the derivative of x of t will be k1 lambda e to the lambda t, since k2 is a constant, and that's equal to lambda x of t plus u. So plugging everything in here from x of t, we can see that this is equal to lambda k1 e to the lambda t plus k2 lambda plus u. So now looking at the left here and the right here, we can see that k1 lambda is equal to k1 lambda, and then we have an implicit plus 0 here, so 0 is equal to k2 lambda plus u. So this differential equation is valid when k2 lambda, or sorry, the test solution is valid when k2 lambda plus u is equal to 0. And that tells us that k2 is equal to minus u over lambda, as we saw over here. Now, we say x of t is equal to k1 e to the lambda t minus u over lambda. Then we plug in the initial condition, x of 0 is equal to x sub 0, and we'll end up with x of 0 is equal to k1 minus u over lambda, which tells us that k1 is equal to x of 0 plus u over lambda. So plugging k1 back in, we'll get that x of t is equal to x of 0 plus u over lambda e to the lambda t minus u over lambda, which matches our solution over here as well. Now let's take a look at a mechanical example. So let's say we have dx dt is equal to 2x plus 2 with x of 0 is equal to 3. So I'm going to use the change of variables method since guess and check should be relatively familiar from the first example. So I'm going to define z of t as x of t plus u over lambda. This is u, this is lambda, this is u. So u over lambda should be 1. So z of t should be x of t plus 1. Then I'm going to say dz dt is equal to dx dt. We know that's equal to 2x plus 2, and that's just equal to 2z. The initial condition, z of 0, is going to be x of 0 plus 1, or 4. Therefore, we can say zp of t is equal to 4 e to the 2t. And then converting back to x, xp of t is going to be 4 e to the 2t minus 1. The last topic we're going to be going over today are functional inputs u of t. So let's say we have the differential equation dx dt is equal to lambda x, but now the u, instead of being a constant, is a function of t. So an example of this is something of the form dx dt is equal to 3x plus t. Another example, dy dt is equal to 4y plus cosine of t. We're not going to derive the particular solution for functional inputs, but you should know what the actual particular solution is. So the particular solution, xp of t, is going to be equal to x sub 0, so the initial condition, e to the lambda t, plus the integral from 0 to t of u of tau e to the lambda t minus tau d tau. Now this entire integral is a function of t. And you can also pull the e to the lambda t out to say that this is equal to e to the lambda t, the integral from 0 to t, u of tau, e to the lambda minus tau d tau. And in the homework, you'll actually verify that this particular solution here, so this entire thing here, satisfies the differential equation. So something like show the derivative of xp of t is equal to lambda xp of t plus u of t. Now we're going to take a look at a mechanical example. So let's say we have dx dt is equal to 2x plus 8e to the 5t. And we're given the initial condition x sub 0 is equal to 3. So we're going to start with our particular solution. We know xp of t is equal to x of 0 e to the lambda t plus the integral from 0 to t u of tau e to the lambda t minus tau. If we look at our differential equation, we can identify that lambda is equal to 2 and u of t is equal to 8e to the 5t, along with x of 0 is equal to 3. So once we plug everything in, we'll see that we get 3e to the 2t plus the integral from 0 to t. U of tau would be 8e to the 5 tau, and then e to the 2 t minus tau. I forgot my d tau. Then we evaluate the integral, and I am going to pull the e to the 2t outside. We get the integral from 0 to t, 8e to the 5t, e to the minus 2 tau, d tau. And this is just equal to e to the 3 tau. So if we take the actual integral, we'll end up with 8, the integral from 0 to t, e to the 3 tau d tau. So then we'll end up with 8 over 3 e to the 3 tau from 0 to t. And plugging in the bounds, we'll get something of the form 8/3 e to the 3t minus 8/3 e to the 0, which is just 1. Therefore, our final solution will be 3e to the 2t minus 8/3 e to the 2t plus 8/3 e to the 5t, and we can simplify this as 1/3 e to the 2t plus 8/3 e to the 5t. The next example we're going to be looking at is dx dt is equal to 5x plus 8e to the 5t, and x sub 0 is equal to 7. So the first thing I'm going to do is identify what lambda, u, and x sub 0 are. Then I'm going to use my particular solution to say that xp of t is equal to 7e to the 5t plus the integral from 0 to t u of tau e to the lambda t minus tau d tau. So when I plug in u of tau, I'll get 8e to the 5 tau e to the 5 t minus tau d tau. And here you'll notice that the 8, or the e to the 5 tau here, is going to cancel with the e to the 5 minus tau here. And the integral is with respect to d tau and not t, so I'm going to pull the e to the 5t out. We get the integral from 0 to t of 8 d tau, and we're going to end up with 7e to the 5t plus the integral here is just 8t e to the 5t. The last question we're going to be looking at today is from a circuits review worksheet. So we're given an RC circuit with a sinusoidal voltage source cosine of omega t, and we're interested in finding the voltage across the capacitor Vc of t. And we're given the initial condition Vc of 0 is equal to 5 volts. So the first part says to write out the KCL equations with Ohm's law and the voltage-current relationship of a capacitor. So first thing I'm going to do is label the currents. So I'll label the current across the resistor as IR, the current across the capacitor as IC. Then I know from KCL that IR is equal to IC. Using Ohm's law, I know the current across this resistor is V of t minus Vc of t divided by R. And then the voltage-current relationship across a capacitor tells me that IC of t is equal to C dVc of t dt. Now let's show that the equation can be put into the following form: dx dt is equal to lambda x of t plus u of t. So I'm just going to copy the differential equation over from the previous part. And I want to put my derivative on one side. So I'm going to put dVc of t dt on one side. I can get this by dividing by c, and I'll get that's equal to 1 over RC V of t minus Vc of t, and this will simplify out to 1 over RC minus Vc of t plus 1 over RC V of t. And V of t was just cosine of omega t. To show that this is actually in the form above, we can show that minus 1 over RC is lambda, U of t is 1 over RC cosine of omega t, and Vc of t is x of t. Now, using this particular solution, write out an expression for Vc of t without simplifying the integral. So let's recall that the particular solution xp of t is equal to x sub 0 e to the lambda t plus the integral from 0 to t u of tau e to the lambda t minus tau d tau. So using all of the values from before, lambda, u of t, and x of t, we can write out the differential equation as, So we also know that x0 is equal to VC of 0, which is equal to 5. So we see that it's 5 e to the minus t over RC plus the integral from 0 to t. U of t is 1 over RC cosine of omega t, so cosine of omega tau all over RC times e to the minus 1 over RC t minus tau d tau. The final part of the question says, what is the closed form solution of the voltage across the capacitor Vc of t? And we're given this hint where e to the at cosine of bt dt is equal to this form over here. So the first thing I'm going to do is copy over the integral and the solution from the previous part. So we know all of this is equal to Vc of t. Then I'm just going to take a look at just the integral. So if we look at just the integral, whoops, the b got copied over. Then we see that we have a e to the minus t over rc, so we can pull that out. And we also have a rc in the denominator that we can pull out. So we're going to pull out e to the minus t over rc, and then we'll be just left with an integral from 0 to t of cosine of omega tau e to the, we have a minus 1 over rc and a minus tau, so it'll be e to the 1 over rc tau d tau. If we look at the hint, we now see that we have e to the at, so a matches with 1 over rc and b matches with omega. So we know that a is equal to 1 over rc and b is equal to omega. Now we have an integral, but this is an indefinite integral with a plus c, and we have a definite integral from 0 to t. So taking all this into account, we can say that this integral is equal to e to the at, so a is 1 over rc, so e to the 1 over rc t, 1 over rc cosine of omega t plus omega sine of omega t all over 1 over rc squared plus omega squared, and then we'll subtract the 0 terms. So e to the 1 over rc times 0, 1 over rc cosine of omega times 0 plus 0 times sine of omega times 0 all over 1 over rc squared plus omega squared. From here, we see that this value is 1. This is 0. So we're going to pull out the 1 over rc, actually, from over here to make our calculations a little bit simpler. So we have e to the minus t over rc. That was from over here. I think I forgot to include it over here. Over, since we're going to pull out the 1 over rc here, we're going to have rc squared. And then the fraction is going to be e to the t over rc cosine of omega t plus omega rc sine of omega t minus 1 all over 1 over rc squared plus omega squared. Then if we put the rc squared into the denominator, we'll see that we get e to the minus t over rc times e to the t over rc cosine of omega t plus omega rc sine of omega t minus 1 all over 1 plus omega rc squared. Lastly, we can bring in the e to the minus t over rc inside, so we'll get cosine of omega t plus omega RC sine of omega t minus e to the minus t over RC all over 1 plus omega RC squared. And this was just the integral, so VC of t, if we recall, will be 5e to the minus RC plus that integral. So over here we have 5e to the minus t over RC plus the integral. So VC of t is equal to 5e to the minus t over RC plus this entire value.